hyperbolas in this. In the first part of hyperbolas, we won't bother to try and get the equations in the correct form. They'll already be in that form. So when we cut the Play-Doh the other day, when we took both cones, and we talked about cones really being the intersection of two lines that are rotated around a vertical axis there, which really gives you two cones. So it's called a double napped cone. When we slice that double napped cone, going through both the top and the bottom half of the cone, you get two cross sections there. And they kind of look like parabolas, but they're really not, because they have certain properties that parabolas don't have. And that graph, that intersection, is called a hyperbola. So a hyperbola, it's in two pieces. We have a vertex, just like you would with parabola. The part that's different, let me just page down a little bit here. The part that's different from a parabola with a hyperbola is not only is it in two parts, but you also have asymptotes for a hyperbola. Hyperbolas are going to get really close to these asymptotes and never cross it. A parabola doesn't have that property. Parabola is just going to keep getting wider and wider and wider. It doesn't have any limits to those values, so no asymptotes. It just, the branches of your parabola goes to positive and negative infinity. So that makes it very different. So we'll go through, there's just pieces of this that, again, we're going to go through and graph. We'll find the center for these, we'll find the vertices, and we'll plot this sort of box thing inside here that will give us the asymptotes. But we're not going to talk about this focal axis, these focus points. We're not going to go through and actually graph them by using those values there. So your very formal definition for a hyperbola, I'm going to show you on the sketchpad simulation here. And this sketchpad simulation is pretty intense here. So collecting the points. So how do you form a hyperbola? Well, hyperbolas are formed when you have the distance between the focal points and a point on this hyperbola, when that difference is the same value. So let me slow this down so you can actually see what the heck's going on here. Let it come around here. Okay, so the distance from this focal point to a point on the hyperbola minus the distance from this point to this focus point to the same point is going to be the same. And really the kind of giveaway is this circle here. These two things are radii, they're the same length. So this distance is always going to stay the same because you're subtracting the same radius. And you don't normally draw this circle here, so this kind of gives away you know, the secret here. Let me move this over a little bit. Oops, wrong thing. Hold on. There we go. So if you look at this one, it's the same thing. This distance minus this distance gives us this same difference, and they're using 8 for that difference. I'm going to move this around a little bit some more. All right, now it's way off the chart. So this distance, that focal point, this distance, if you subtract those two values, it gives you the same sort of bold difference there. And again, it's way more detailed than we're going to go into. It is kind of cool to see, you know, where it actually comes from. And if we do the same thing on the other branch of the hyperbola, those differences, again, are the same values there. So this focal distance minus this distance gives you the same value, that same 8. So if we look at this in terms of how the heck we're going to go through and graph these things, we're going to come up with two parts. We're going to come up with the, obviously we'll come up with the center, but the vertices are key, and then these asymptotes are key. And that's how we're going to go through and graph these. So we're going to jump right into how to graph these. So two different ways that these things can happen, these hyperbolas. Either they open to the left and to the right, or they open up and down. And it's easy to see which way they're going to do that. If the x squared is positive, so that first term is positive, usually it's written in that form, x is first and then y is second. If that's the case, x is first, it's going to open left and right. If the y squared over 16 was first and then it was minus x squared over 25, then it opens up and down. So it's not too difficult to figure out which way they're going to go. So we'll find all the pieces for this, and I'll show you how to do this little graphing box thing here, and they're not too awful to graph. So for this one, just like for ellipses, and if you notice the equation is almost the same as the equation for an ellipse, except it has a minus sign in between. So the center for this one is at 0, 0. me get rid of this sketch pad thing here. Here we go. So my center is at 0, 0. My values for, oh, and the other thing is A is always the first value. It's always under whatever the fraction is that is first, it's positive. So my A value then would be plus or minus 5. And I do need the B value. B can be larger or smaller. It just depends on the number they give you there. It's going to be 4. So from this, we're going to plot the center. So the center's at 0, 0. And then since the x squared is first, it's going to open left and right. Remember, they're in 2 branches there. So from that center, since my A value is underneath the x, I'm going to go left and right 5. And then I'm also going to go up and down my B value, which is 4. Right, you can kind of put points there if you like. And what we're going to do is we're going to form a box. And we're going to connect the segments that would contain those points there. So vertically and horizontally here, we'll connect these points. And I'm just connecting them with dashed lines because it's not part of the graph there. It's just going to be something that helps us to create the graph. And then I'm going to go through and connect the 2 endpoints of the diagonals of the box there. So if you connect these diagonals, these are actually the asymptotes. And it saves you from coming up with equations and things like that. So these are my asymptotes then for my graph. And they're actually slant asymptotes, but we don't need the equations for it. And then the vertices, since this is going to open left and right, that's a vertex, and that's a vertex. And it's at 5, 0, and negative 5, 0. The top and the bottom points, these 2 points here, these are nothing. They only give you the dimensions for the box there to come up with the asymptotes. And then the actual hyperbola goes through the vertex, gets close to that asymptote without crossing, gets close to the asymptote without crossing. And same on this side. All right, so it gets close to those without crossing. And everything else, the box and the asymptotes there, like I said, are dashed lines because they're really not part of the graph. Just the blue branches there are the actual graphs. So that's what you're going to do. Plot the center, the A and the B values, make the box and the asymptotes there. So let's try another one here. So if you look at the next one, example 2, this one is not in standard form. So just like we had for ellipses, we'll put that in standard form by setting it equal to 1. So if I take that equation and I divide everything by 36, have y squared over 9, x squared over 4 equals 1. And now you notice that the y squared is first, which means this one's going to open up and down instead of left and right like the other one. Center is still at 0, 0. A value is still first, plus or minus 3. It happens to be larger, but it doesn't have to be. B values are plus or minus 2. So my center is at 0, 0. My A value is 3, and since we said it's opening up and down, we're going up and down 3 units. Those are actually the vertices. And then left and right 2, that's just going to help us create the box. Let's do a lighter color here. Those endpoints there, and then we'll draw the diagonals in. Again, a dashed line because it's really not part of the graph. I shouldn't say it's not part of the graph. It's part of the graph. It's just not solutions. Solid lines mean they're solutions. We said this one's opening up and down. So again, it gets close to those asymptotes without crossing. Go. And we really don't need the equations for the asymptote. Center and vertices are fine there. All right, and then the last type that we're going to look at today are hyperbolas where the center is not at the origin there. But same idea. So if you look at this, same as we did with ellipses, h and k are the values for the center. Either the x squared term is first or the y squared term is first. Opens left and right, opens up and down. All right, same idea. This looks so scary. You don't have to memorize all that. We'll just shift everything. It works out lovely. All right, so let's find our center for this one. So the center, oh, remember HK. So H is always with the X, K is always with the Y. So my center is -2, +1. A value is always the first term. In this case, it's 3. My B squared term is the second term. In this case, it's 4. So this one is, the A isn't the larger number for this one, which is fine. So if we go through and we plot that center at -2, 1. And then from that center, since the Y is first, this one opens up and down. I usually write that so I remember which way to go for A. So up and down 3. And then left and right 4. 1, 2, 3, 4. Connect all of these to create the box. Draw those asymptotes in. And again, these are my vertices. I'll come up with the coordinates for those in a second here. We said it opens up and down because Y is first. Okay, and then the vertices from that center, -2. From 1, we went up and down 3 units. So it would be -2, 4, and -2, -2. So you'll see a couple like that you have to go through and do. And that's it.